if you think about the Thevenin equivalent circuit, which, to remind ourselves, looks like this, with a Thevenin voltage and a Thevenin resistance. If you think about that, then you might think, well, I can apply a source transformation, and I can turn the voltage source into a current source. And so this would give us another equivalent circuit that we could use. And this one is called the Norton equivalent circuit. And in particular, we label the current source as IN for the Norton current, and we label the resistance as RN for the Norton resistance. And of course, we know from the rules of source transformation that the Norton resistance must be equal to the Thevenin resistance. So all the tools that we just learned for how to calculate a Thevenin resistance will also continue to apply here for these Norton equivalent circuits. And we also know that the Norton equivalent current is related to the Thevenin circuit as follows. So it will be Thevenin voltage divided by Thevenin resistance, right? That's the rules of source transformation. But we could also go directly to the Norton equivalent circuit. So to find the Norton equivalent circuit directly, then here is what we would do. Same type of analysis as before, where we would need to find the open circuit voltage and the short circuit current, so VOC and ISC, open circuit voltage and short circuit current. We can then read off the Norton equivalent current as just being the short circuit current. And in fact, you can kind of see that directly from this circuit diagram, right? If I was to short these terminals together, then the short circuit current that would flow here is obviously that current due to the current source. So ISC must be the Norton equivalent current. And of course, the resistance, there's really, again, only one way to calculate a resistance given that the things we measured were voltage and current. So Rn will be the Ohm's law combination of the things that we measured. And again, this is the same as the Thevenin resistance. So let's do an example. So the problem that I have here is to find the Norton equivalent circuit looking into these terminals. So the Norton equivalent circuit looking into these terminals. Now, a few strategies that I could follow. Basically, I need to find a short circuit current and an open circuit voltage. So step one will be to find the, let's say, open circuit voltage. I'll do that one first. So to do this, what I'm going to do is redraw this circuit and then calculate this open circuit voltage. Now, the voltage that I'm actually trying to analyze here is, of course, this voltage here, this VOC, which would be the same as the voltage across this 12 ohm resistor here. Now, a few ways that I could analyze this. I could do a nodal analysis where I could define, say, a reference node and then work from that. So define a reference node here, define a node, and then another node, and then another node, and proceed in that way to do the analysis. But that one will probably take a little while because there'll actually be quite a few nodes there. So a simpler way to analyze this would be actually to do a mesh analysis. So if I was to define some meshes, so if I had a mesh current here, let's call that I1, and then another mesh current, let's call that one I2, then this is actually really nice because the mesh current I1 is obviously defined by this, this source over here. So I actually get kind of immediately that I1 is just 15 amps. And so that's a really nice starting point. And then I can write my equations around mesh 2, so I can do KVL at the mesh labeled as I2, and here's what I'll get. So I'll choose a starting point, let's say top left corner of that mesh, and I will have that 2 times I2 plus 12 times I2 plus 10 times I2 plus 8 times I2 minus I1 is equal to 0. Of course, once I know I2, then I can use Ohm's law to calculate this open circuit voltage across the 12 ohm resistor. So that will be the strategy that I'm following. I know the value for I1, so I can substitute it in. That was 15 amps. And I can collect some like terms on the left-hand side. So 2 and 12 will give me 14, plus 10 will give me 24. So I have 24 I2 plus 8 times I2 minus I1 was 15 is equal to 0. To calculate this, so the 24 plus 8 is going to give me 32 times I2, and then 8 times 15 is 120, so that would be minus 120 is equal to 0. So I2 is going to be 120 divided by 32, so 120 divided 32 is 3.75 amps. So then I can calculate what must be this open circuit voltage, so VOC here will be just the voltage across this 12 ohm resistor. So looking at the polarity, I have the current flowing from the positive to the negative side, so that's the normal direction of current, so I have just positive V is IR. So positive V equals IR will give me 3.75 times 12, so just that times 12 is 45 volts. So VOC is 45 volts. All right, let's make a note of that one, and we will keep on going. So the next step would then be to find the short circuit current, to find ISC. So again, I'm just going to copy my circuit and then redraw it and find what will be the current when I actually short these terminals together. So I'm interested in what would be this current here, ISC. Now, when I analyze this, I should recognize that this 12 ohm resistor here cannot contribute, right? So any current that is approaching this junction is going to prefer the short circuit, right? It will never flow through that 12 ohm resistor because there's a short circuit which is an infinitely more attractive path for that current to flow down. So I can basically like cross off this resistor from the circuit. It's not going to be present and it's not going to contribute in any way. So then my question is, well, what is the current that actually flows through that particular branch? And you could analyze this as a current divider circuit. So I have 15 amps that comes in and flows down through that branch, and also down through this branch over here. You could also approach this by doing a like a mesh analysis on it. So let's do the mesh analysis. I think it's a useful one to actually practice. So let's write here I1. And then our second mesh here, well, that one's just going to be ISC. It's the current that we're actually trying to find. So same as before, we have that I1 is going to be 15 amps. Let me just draw that one a bit more cleanly. I1 is 15 amps. And then I will do Kirchhoff voltage law around the mesh labeled with ISC. So that will give me, starting at that top left corner, that will give me 2 times ISC plus 10 times ISC plus 8 times ISC minus I1 is equal to 0. But I know I1 is 15, so I can substitute that one in straight away. So this will give me the following. ISC minus 15 is equal to 0. So that's 20 ISC minus, so 8 times 15 was 120. That's equal to 0. So ISC will be 120 divided by 20, which is 12 over 2, which is 6 amps. So now that I have my short circuit current and my open circuit voltage, I can write down my Norton equivalent circuit. So step 3 here will be identify that my Norton current is my short circuit current, which is 6 amps, and my Norton resistance will be open circuit voltage divided by short circuit current. Open circuit voltage was 45 and short circuit current was 6. So this would be 45 divided 6 is 7.5 ohms. So now I can draw my Norton equivalent circuit. So it has a current source in parallel with a resistor. Resistor is 7.5 ohms and the current source is 6 amps. So that there is the simplified version of this circuit calculated as a Norton equivalent circuit.